All right, welcome back, everybody, to the sixth lecture. I got a lot to get through, and first thing I want to say, this is a point in the course where it starts to get harder because a lot of concepts collide. We've just taken ordinary regression and done nothing but add some more terms. It seems simple, but suddenly it's a lot more complicated. So if you're feeling confused, that is only because you're paying attention, and you should feel perfectly happy about that. It's a good sign that you're confused. If you weren't confused, I would be worried. So we're all in this together, and you should realize that if you don't understand something in lecture, a lot of this knowledge comes from performing it. You have to go through and run the examples. It's like learning a martial art, to use a wholly inappropriate metaphor. You can't just watch Jackie Chan movies and learn Kung Fu, right? I've tried. It doesn't work. And you should watch Jackie Chan movies, but you're not going to learn Kung Fu from them. You have to actually throw some punches and take some punches as well. And learning statistical inference is like that. I should find a better metaphor than martial arts, but I think you know what I'm trying to say, right? So don't be concerned if you're confused. That's perfectly normal. I've spent decades being confused about quantitative methods, and look where it got me, right? Okay, so we're going to pick up exactly where we left off with this mechanical but very important issue about how to include unordered categorical data in a regression. And I had ended last time by presenting dummy variables or indicator variables, which is the traditional form. To do this, if you use an automated tool in R or any other statistical package, it will probably code dummy variables for you automatically. There are a lot of downsides to using dummy variables. If you're coding the model yourself, it's nearly always better to use an equivalent but alternative form called an index variable. So you take your unordered category. Here it's just sex, and there's just two categories within it, male and female, and you make it into an index. An index is a variable that starts at 1 and counts up from there. And each unique number in that corresponds to a different categorical value. This has a lot of advantages. The first advantage is that you can assign the same prior to each category. So you can have the same pre-data expectation for both males and females in this version of the model, where you can't with a dummy variable, because you've got one of the categories is coded as a difference from the other, and then you have to have a prior on the difference, and that makes setting the prior harder. The other reason to do it this way is that as you get more and more categories, the model looks exactly the same. You don't have to change anything except how many unique values there are in the index variable. So if you're doing something like a regression on countries, I don't know how many countries there are in the world. Probably nobody does, right? It changes every day. But there's a lot. And you don't want a dummy variable for each of them, right? That's madness. So the index variable approach grows really nicely. It's also the foundation of multi-level models. And so if you get used to doing it this way, you can slide very naturally into using random effects when we get there later on in the course. But this is perfectly mathematically equivalent, aside from the issue of the prior, with the dummy variable approach. And you can code this in CLAP just by using this bracket notation. Once you've created the sex variable, which is an index, it contains 1s and 2s for the anonymously labeled sex 1 and sex 2. And the bracket notation means A for each sex in the linear model, and then in the prior as well, you say you want an alpha for each sex, and that creates a vector of alphas, 2 of them. So when you run this model, as you see on this slide, and you get the Précis output, you'll get 2 alphas. There's alpha 1 and alpha 2. And if you had 100 different sexes in there, well, you could have 100 alphas. And the model code will stay the same. You don't have to change anything. This is a really convenient feature of this way of doing things. The awkwardness, of course, is you want to make inferences about differences between categories. So you need to compute those. These are called contrasts in psychology. In biology, we just call them differences. So once you've got the posterior distribution, you can convert to any other parameterization of the model after you've approximated the posterior. You don't have to rerun the model. So in this case, if we want the posterior distribution of the difference between the two sexes, this will be the average difference in height, where this is height data. You just extract samples from the posterior, That's the top line of code on this slide. The second line, I compute the difference by just subtracting each sample of alpha comma 1. Why is there a comma there? This is for every sample from the posterior, right? The 1, at the number after the comma is which of the alphas. The number before the comma is which sample. So if you leave it blank, you get all the samples. So for every sample, this code says, for every sample, subtract the second alpha from the first. And store that difference in a new symbol called diff_fm. And I'm going to stick that in the post. It's in the posterior, because there's a posterior distribution of this difference. And then I can just pass that whole thing to Précis. Précis takes a whole bunch of objects. It likes things, right? I use it all. I wrote it for myself years ago to summarize stuff because I hate p-values and I wanted a summary function that doesn't show them. Right? They burn my eyes. Really, just burn my eyes. No, I joke. I don't like them because they contain no information of use. So I just clean up my screen. The other thing is I don't like a million decimal places, right? So 2 decimal places is usually fine. And so when we look at diff_fm here, the posterior mean is about minus 0.8, and then you get a compatibility interval there as well. And this is often we want to make inferences about that difference. And so if you had 100 categories, you could calculate this difference for any pair of them you like, right? They're all there in the posterior already, right? All the comparisons already exist inside the posterior. You just have to compute the ones you're interested in. Okay. In the chapter, there's an example where we look at the primate data again, and I show you how to do this with multiple species. So that'll help you understand what happens when there's more than 2. And there's a code example, and I also show you how to include more than 1 index. So you can have, I forget what I did, I had species, and then I had Hogwarts house or something like that. And the Slytherin has a lower mean, something like that happens. So please look at the code, and we'll be using this kind of coding in future examples quite a lot. It's much more natural, I think. It's easier to set priors for, and if you ever need the difference, you can still get it back out. Unfortunately, it's just not the default in most statistical software. Okay, let me switch gears to the meat of today's lecture. I'm very excited about this lecture because there's a lot of new content that I have not subjected an audience to before, and I'm going to have fun with this now. I think it's an interesting feature of the scientific literature that there seems to be a negative correlation between surprising things and true things, right? So newsworthy studies seem to turn out to be untrustworthy at a very high rate. And the reverse is also true, that the most trustworthy science is incredibly boring, right? Another cell biology paper on some ion channel. It's probably right, but it puts you to sleep. You're halfway through the abstract and you're asleep, right? Meanwhile, here's my favorite example. It's a paper from the prestigious journal, PNAS. The P stands for prestigious. Prestigious? No, it stands for proceedings. Entitled, Female Hurricanes Are Deadlier Than Male Hurricanes. There was a response. You can read the title of the response for yourself here. This is almost certainly not true. What's the idea? Now, hurricanes don't have gender, right? You might be thinking about that. But they get names. And the National Weather Service in the United States likes to name hurricanes because it's easier to refer to them by names, I guess. And they have this convention of alternating male and female names. And I forget when this started. And there's a list, actually, and they just go down the list, but it alternates male and female. And so you can regress. These data are in the Rethinking package if you want to play with them, data hurricanes. I'm here for you to entertain you. If you do a terrible regression, yes, there's a correlation between gender of name. Female hurricanes have killed more people historically. But it's not robust to the model specification. And secondarily, there's no plausible mechanism by which this could actually work, right? The idea in the paper is that if you name a hurricane with a female name, people don't take it as seriously, and so they don't evacuate. This is historically false stuff. But this got a lot of press. This was written up in lots of places. It spread around the internet very quickly because it's like, wow, if true. You know that phrase? Right? So a lot of science is transported by the big if true things. And a lot of these things turn out not to be true. Now, this is a bit silly, and that's why I use it as an example. But there's lots of less silly science that's done as rigorously as possible. And still, it seems like the newsworthy stuff turns out to be false at very high rates. A lot of epidemiological work is like that, right? It seems like every week coffee is either going to make you live forever or kill you. Yeah. I don't know if cell phones are good or not. Whatever. Here's a study that I think is quite interesting. And some of you will have heard of this Arsenic Life paper that came out, it was a couple years ago now. So this is a lake. Those of us from California know this, Mono Lake. Mono Lake has very high naturally occurring levels of arsenic. Arsenic is bad if you're a living thing. And if you're a cyborg, maybe you don't care as much. But why is it bad? Because arsenate mimics phosphate. And phosphate's extremely important for all kinds of cytoplasmic reactions. It's also part of the spine of DNA. And if you get arsenate in your cell, it replaces phosphate and then things break. It's very bad. This is why arsenic is a deadly poison. It's a cellular mechanism. Mono Lake has really high levels of arsenic, and there are lots of life forms there that get along and reproduce. And the question is, how do they do it? What's the evolutionary processes that they're adapted to arsenic, to toxic environments? So this is Dr. Felicia Wolf-Simon had published a quite newsworthy study which had evidence that there were bacteria in Mono Lake that were actually using arsenic to build their DNA. NASA got really, really excited about this because it means that you could potentially get life in places with low phosphate concentrations. And arsenic is, galactically speaking, much more common than phosphate. And so this was a big deal. Since then, it's turned out probably not to be correct. But it was a rigorous study. There was nothing like scientifically, there's no misconduct here. It's just, it's probably not true, but it would have been really big if it were true, right? But it probably wasn't true. There's lots of stuff like this that seems to be the case. And then the flip side, I won't give you an example, but the flip side is, yet another fruit fly paper, right? Which is probably true, but really dull. So what's going on here? Now, lots of people have theories about why this happens. I don't think we need any elaborate theory to explain this impression that we all have, which I think is true, although I don't have a big data set to prove it. All you need to get a negative correlation in the published literature between newsworthy things, that is things that are clickbaity, right? And trustworthy things, which means things that turn out to be true in the long run, is peer review. It's all you need. So bear with me. Here's a simulated example, and chapter 6 begins with some code. You can play with this on your own. Imagine that either at journals or at grant review panels that fund the work in the first place, you care about both the impact of the work, that is its newsworthiness. The public will care and it will make a difference in the field. That's what makes things newsworthy. Yeah? Big if true. Yeah? But you also care about rigor. You care about the trustworthiness. And we care about both of those things. And we should. There's nothing wrong with caring about newsworthiness, right? We should be doing science that matters. Yeah? I don't think there's anything wrong with that motivation. If you care about both, then they're compensatory. And a study can get published or get funded if it is sufficiently trustworthy or if it is sufficiently newsworthy. So even if there's no correlation in the production of science, in these things, post-selection, there will be a negative correlation between them. Right? And so this is the simulation that I plotted here. This is a perfect Gaussian cloud of random imaginary studies, say grant proposals, in which there is no correlation between trustworthiness and newsworthiness at all. The code's in the chapter. I encourage you to play with it. And then there's a threshold of the sum of newsworthiness and trustworthiness above which you get funded. That's why it's compensatory, right? One can compensate for the other because both matter. And then the blue are the ones that get funded, and the line is just a regression line drawn through them. And the correlation here is minus 0.8. You can get extremely negative correlations between these criteria. But this is, if you think this is a causal thing, and it's telling you something about the nature of how science is generated, you're wrong. Right? Well, actually, I don't know in the reality why this is true. This is just an imaginary example, right? It's just that you can't know from this correlation necessarily what's happening generatively because of the selection effect. Now, why am I telling you this story? It's not to depress you, right? Rather, it's to set up a fundamental lesson about how multiple regression works. This happens inside of multiple regression models. Multiple regression models, when you stratify on a predictor, it's like a selection effect. You're creating subpopulations, and those subpopulations can have spurious correlations like this is a spurious correlation. It's not telling you how science is generated. It's telling you about a selection process. Conditioning on a variable in regression is a selection process. And that's what I hope to transmit to you today, some understanding of that and why it is our responsibility to think about the possibilities of this. And we shouldn't just add things to regressions and hope it all works out, because sometimes it won't. So this effect is called the selection distortion effect, or Bergson's paradox. It's extremely common. It happens a lot, and it happens organically, if you will, inside of regression models. I want you to think about regression. Regression is an incredible tool, these geocentric models. It's valuable, and we should never give up on it. It does a lot of really good heavy lifting in inference, but it's an oracle. It can see stuff that we can't. It automatically finds the most informative cases. It ignores the ones that aren't informative. It deals with all this partial correlation structure. It's actually amazing that the universe is designed such that this works out. It's incredible. It's an oracle, but it's like a historical oracle, the Oracle of Delphi. The Oracle at Delphi could ruin your civilization. At any moment, the Oracle at Delphi could get a mood and decide, no, the prince has to die. Right? Just whatever the Oracle wants to say. The Oracle is not benign, even though the Oracle is wise. And this is how a regression is. Or if you want to think about genies, in the more Middle Eastern tradition, right? The genie is powerful, but you have to give it your wishes very, very carefully, because it will take them extremely literally. And that's how regression is. It will answer the question you pose to it, but it will take your question very, very literally. And so you have to understand the language of the genie of multiple regression. And that's what I'm aiming to help you do here. So I want to contrast this kind of cautious approach and worrying about selection effects and such with the way I think regression is sometimes, well, I don't want to say it's taught this way, but it's practiced in the sciences quite often like, well, we've got all these potential confounds and let's just add them in, right? And you see these big regression tables in papers. I call this table 2. Right? Table 2 in each paper is all the controls they've tried, right? And sometimes coefficients change, and it's all an uninterpretable causal salad, right? And that's bad. Adding variables to model can create confounds, not just remove them. So it's not harmless to add things, and you need some justification to add a variable to a model. And that's what we're going to talk about today. The sink here is because there's this expression, the kitchen sink, right? Okay, so let me try to give you some framework, and I'm going to fill this in throughout the rest of the lecture and give you some examples. And this chapter has all the code. I'm not going to show you all the code in the lecture, but the chapter has all the computational, all these examples computed out for you. And we're going to use a lot of simulated examples because those are the only cases in which we know what's true, right? So actually, there's this benign fact that there are only 4 kinds of confounds at all. This is nice, right? This is a provable thing. In this, at least in this simplified causal structure that I've been showing you, this DAG view of things, where you've got directed acyclic graphs representing a causal model, there are only 4 kinds of confounds. That's it, and there's no other kind of confound that can ever arise. Well, there's residual confounding. We'll talk about that later. So sorry, there's more. But ignoring those things, like measurement error, these are the only kinds you get. And they are the fork, the pipe, the collider, and the descendant. And I'm going to explain each of these to you and give you an example and show you what they do. And then at the end of the lecture, we're going to loop back to this slide, and I'm going to explain to you how you deconfound each of them. There's a method for deconfounding each. And if you know the causal graph, which of course you don't, but hey, I mean, this is still better than no news, right? If you know the causal graph, you can either deconfound, know which variables you need to add to the regression to remove the confounding, or you can conclude that it's hopeless and you can't deconfound. And that's good, right? Knowing that you can't get the answer from the data set is an important achievement in science, right? Rather than making stuff up. Yeah. So we're going to come back to this, and I'll define each of these in order. Let's start with the fork. The fork is the most famous confound. It's in many cases the first and last example of confounding that people receive in their statistics education. This is a variable that is a common cause of 2 others. We've had an example of this already. This was the age at marriage confound, right, where median age at marriage created a fork. It causally influenced both divorce rate and marriage rate, and so it created a spurious correlation, a confound, between marriage rate and divorce rate. You remember that from Monday? It was a long time ago, before the snows began, right? And so this is why I draw it up here. This is the fork. The idea is you've got three variables, x, z, and y. In all of these figures, the idea is that you're interested in the association between x and y. In particular, you're interested in the causal influence of x on y. Z is this third variable that could be a confound. And here is, if z is a common cause of x and y, it'll look like there's an association between x and y in a regression unless you include z, condition on it. So in the fork, you de-confound the fork by conditioning on z. And this is, I'll explain later, what this does is it shuts the fork. There'll be some language later where you get time. It's a weird expression, shut the fork. Break the fork, bury the fork, I don't know. We need a metaphor. But it removes the confounding. It stops information flowing from x to y. It shuts the path. We're going to talk about paths in these diagrams later on. There's this notation. You'll see we won't use it very much, but I want you to recognize it at the bottom of this slide. This x and then this weird, I don't know, science fiction symbol here. Y, that means independent of. So x is independent of y, or d-separated, d for dependency, dependency separated from y, conditional on z. So once you learn z, there's no remaining association between x and y. That's what that notation means. And you'll see this in a lot of papers, especially in epidemiology, and it's a bit confusing unless you know what's going on. But that's all it means, is that x is independent of y, conditional on z. The second one is a pipe. The pipe is a lot like the fork. We haven't had an example of this yet, though, so I'm going to explain this to you, and then we're going to have an example. Okay? So the pipe is a case in which there's a mediation. The psychologists are going to know this, right? A lot of the biologists too. But psychologists, this is like your first thing. It's like mediating variables, and mediation analysis. So here we're interested in the causal impact of x on y, but if in reality it's mediated by a third variable z, if we condition on z, then we don't notice the causal impact of x on y. It actually knocks it out. You might want to do that if you're testing for mediation, right? If you want to see if it's there. Or you might do it by accident, which I think happens a lot in regression. In an observational study where you don't know the causal graph, if there's a mediating variable and you control for it, then you will control away the real causal variable. Now, that's an example I'm going to give you in a second. So x causes z causes y is the way to read this thing, or z mediates the association between x and y. If you condition on z, the middle variable, just like with the fork, then you remove the statistical association, the dependency between x and y. Right? Notice that with data alone, you can't tell the difference between a pipe and a fork. You can't see the causal graph in the data. You always need something more than the data to tell what's right. That's why the machines will never replace us. I hope. Yeah. Does this make sense? Yeah? Okay. Of course, in reality, pipes and forks behave very differently. They're very different causal relationships. Let me give you an example of a pipe and a major inferential threat, a kind of confound that I think arises. It arises both in experiments and observational studies, but probably more often in observational studies where people just start throwing in covariates to control for stuff. So this example's in the book. I'm not going to give you code here, but I'm going to walk through it conceptually with you. So the confound that gets created sometimes goes by the name post-treatment bias. What does that mean? Post-treatment is z. The treatment is x. It's something you've done to a system because you've experimentally manipulated it, or nature has manipulated it, and you want to assess the causal influence of that treatment on some outcome of interest, right? X and Y. Post-treatment variables are the variables that arise as a consequence of the treatment and are on the path, on the pipe, to the outcome of interest. And there could be a lot of them. Lots of things happen, right? You add arsenic to a lake, lots of cellular processes kick in, eventually cells die. But there's lots of mediating stuff you can measure along that path about what happens. So post-treatment bias is the regression confound that arises when you're not aware of this causal relationship, that some mediating variable is on the path, and you control for it, thinking you're testing for a confound, a fork, but you're really knocking out the mediator, and you end up inferring the treatment doesn't work. And I think this happens in embarrassingly high percentages of the time in the sciences, because people don't have a causal model of what's going on. Let me give you an example where it's fairly obvious, I would think, and you would never do it, right? But just so you understand, all the code to simulate this example is in the text, and I encourage you to walk through it, because there's also a regression model there, and you can think about parameterizing and choosing priors on that regression model. That's also worth doing. But I'm not going to do that in lecture. I apologize, just the sake of time. Yeah. But it's good practice, and you should do it. So let's imagine an experiment where we have a greenhouse experiment with plants. Sorry, I used to be in agricultural school, and so I had lots of collaborators in greenhouses, and I did lots of stats consulting with people doing greenhouse experiments. So it's history. This is where it comes from. And I have botanist envy. Plants sit there and they wait to be counted. Right? It's much nicer than studying monkeys, which don't sit still. So we're a big problem in these greenhouses is fungal growth. They're humid places, right? Fungus loves it. And so you need some antifungal treatment to help them grow. So we've got some hypothetical antifungal treatment, and we're going to randomly assign plants to a control and to the fungal treatment. The causal model that I present here is initial height and the presence of fungus cause your final height, H1. So H0 is the height of the plant when we assign them to the treatment groups. Fungus reduces growth. Taller plants initially are also taller later. Both of these things interact. Two arrows enter a variable, then they potentially interact. The antifungal treatment is upstream causally from the fungus, right? It influences fungus, but it doesn't influence height directly. It could, but I'm asserting it doesn't. There could be a direct impact of the treatment on height, right? Because it could also affect the plant's growth directly. What happens here in a regression is if you measure fungus, and you should, if you're doing this experiment, you're doing it well, you'll measure the intermediate variable. You'll measure fungus, because this is how you test for mediation, right? You want to know this first arrow from T to F, because that gives you the direct impact on the fungus, right? But of course, what you're interested in, if you're going to use this in your greenhouse, is the full path from T to H1, right? That's the causal impact. If you condition on F, it'll look like the treatment doesn't work. The correlation between treatment and plant height will vanish. And the code to do this is in the book, but I think you can probably see it from the diagram. Why does that happen? Because if you condition on the fungus here, you block the pipe. You close the pipe. Information can no longer flow along the path from T to F to H1 in that case. And so in this case, you would never do this, right? You would measure F, because then you do another regression just looking at T to F, and you say, oh yeah, it reduces fungal growth. Look, the amount of fungus on plants in the treatment group is much lower, and then you do another regression leaving fungus out to get the treatment effect, which is going to be lower than that, right? Because some plants without fungus still don't grow very well. There's other things that affect the plants going on. Does this make sense? Yeah? In observational studies, the terror is real. Because it's not this clear. There's not an experiment, you're not sure what the mediating paths are, it's hard to measure things, and then the causal salad temptation comes in, right? You've got a big list of stuff that you know about the cases, and you can add them into the regression and see if any of those is a mediating variable. It'll knock out your variable of interest, and you might conclude that, no, that thing doesn't actually matter, it's really this other thing. These debates happen. Let me give you an example that is potentially a little bit controversial, that's why I have fun with it. There are lots of debates about the wage gap, right? Gender wage gap, racial wage gaps in the U.S., and what the causal diagrams are. And a frustrating thing for a statistician with these debates is that no one wants to put up a causal diagram about what's going on. And you'll hear lots of times is that if you condition on career choice, there's no wage gap, which is basically true. I mean, there's still some differences, but conditional on occupational choice and hours worked, there's basically no wage gap. And that's true, but that doesn't mean that gender and race is not causal of the wage gap, right? Because there's streams. There's a bunch of arrows in this. It's just like the greenhouse experiment. You don't then conclude there's no discrimination or there's no problem. just because it's downstream. There's some downstream thing that knocks it out. Yeah? Does this make sense? It's an example that I use a lot too with grant funding. There are big differences in the amount of grant funding by scientific field, right? So psychology gets way less than cell biology, newsflash. Yeah? So if you look at funding rates of men and women in the sciences, say in the ERC, just naively, women get way less grant money than men. But if you condition on field, men and women are funded at about the same rate. Because it's downstream, right? It's gender influences field choice, the choice of the field you're in, and then some fields receive less funding than others. And so there is inequity in outcomes, but you have to figure out the causal diagram right to know what to do about it. Yeah? Or if you want to do something about it. Not everybody cares about that issue, but I do. And I think if you want to fix that and make more equitable outcomes, then you have to do upstream from grant review. Does that make sense? Sorry, this has been my little sermon for the day. But yeah, quickly, question.
Just to make sure. So in such a model, you would still see the direct effect. So each arrow would correspond to a significant effect if we want to.
Well, I refuse to use, the question was each arrow would confirm to a significant. I refuse to use the word significant.
I know.
But there can be, you can make a simulated example like I do in the text where there are those arrows exist. There are causal influences at every step. But conditioning downstream means that you statistically won't see the upstream effects because there's no information remaining to learn from them once you know the ones downstream.
So not only you wouldn't see the association between status and income, but not even the association between status and job, for example.
Right.
You will see.
You won't see that. Once you condition on job in this sort of thing, all of the upstream effects have been taken into account. They're already in job. And then job affects your wage, but there's all the other stuff that led you to a job. And it's the question, and those are the treatments, right, in this outline. Does that make sense? Yeah, but all the arrows can exist and be real, and you'll still just miss them all. Okay.
Richard?
Yeah.
Can I ask a question about the fork versus the pipe?
Can we, is it quick?
Well, I mean, it seems like in the pipe situation, the X and the Y are, potentially you can misrepresent the relationship by conditioning on the Z.
Yeah.
Intermediate. But the opposite is true, isn't it, in fork? That you'd be misrepresenting X and Y by not conditioning on the Z. Is that right?
Let's come back to this. I know what you're asking, and there's a denouement coming where I try to tie all this together, and we're going to do something called the backdoor criterion that puts all this together, right? I know now everyone's thinking of a Howling Wolf song or something, but at least the Americans are. Doors, maybe the Doors, from the Doors. But, okay, let's do the collider. The collider is explosive. It's great. It's my favorite confound. This is where the selection effect at the beginning of the lecture comes from. So a collider is a case, it's like the fork but reverse. So in the fork, Z is a common cause of X and Y. In the collider, Z is a common result of X and Y. Both X and Y influence Z. It's a collider of X and Y. So you could say X and Y are jointly cause Z. X and Y are really independent, right? They have no causal linkage between them. But if you condition on Z, it creates a statistical association between X and Y. A spurious one if you're trying to make a causal inference. This happens all the time, I think, and it's very dangerous. There's lots of cool effects that arise from conditioning on colliders. One of them is the example I gave you at the beginning with the trustworthiness and newsworthiness. Selection for a grant or publication is a collider of trustworthiness and newsworthiness. It arises from both. They can have no statistical association in the general population, but conditional on Z, on being published, there is a statistical association between the two. But it's spurious, which means it doesn't inform you about causal relationships. I'm going to give you more examples. Colliders are the hardest conceptually, but they're also the most hazardous, and they're really worth understanding. And they're common, right? They have to happen. Just depends upon which variable you're looking at. They will happen in all causal graphs eventually. So another way to think about this, as I put at the bottom, learning X and Z reveals Y. Right? So this is the thing about colliders, is there's this finding out effect of learning one side once you know the collider. Let me give you some examples, some heuristic examples to maybe help. So imagine we've got a light, and it's controlled only by a light switch and the presence of electricity. And now you're thinking, but there's a light bulb. Shh. I know there's more, but this is a conceptual example for learning, right? So now imagine I tell you that the switch is on and the light is off. Can you tell me whether the electricity is working or not? Of course you can, right? Because it's logic. This is how colliders work. This is the finding out effect. It also works in continuous systems as well. It's just harder to give examples where it's like that. But it works for continuous variables as well. And I'll have an example that will work through. On the other side, right, if the electricity is on and the light is on, the switch is on, right? Because otherwise the light wouldn't be on. You see how colliders work? So when you get confused about colliders, think of the light switch. Or some other example that you like. Yeah, but this is the basic logic of how they function. So here's the trustworthiness, newsworthiness idea. Newsworthiness and trustworthiness both influence being published because it's compensatory. So if I tell you there's some study that's not very trustworthy, but it's been published in Nature, can you tell me how newsworthy it is? Yeah, you know it's clickbait, right? You know it's on BuzzFeed already. Yeah, sorry, I shouldn't pick on BuzzFeed. But BuzzFeed is definitely not the worst part of the internet. Right? It gets worse. There are lots of effects like this that happen all the time. Here's one that I quite like. This comes from Matt Hahn, who's an evolutionary biologist on Twitter. This is an obsession of his, like it is with me, is collider effects. We're here in Europe, but everybody here has heard of basketball, right? There's this weird sport we play in North America. Involves a court and dribbling a ball and throwing it. It's a great sport. And being tall is definitely, causally speaking, an advantage in basketball. Because there's this hoop and it's elevated above the height of any like normal human being, and so you have to, the taller you are, the easier it is to score field goals. They're called field goals. And nevertheless, conditional on being a professional player, there is no correlation between height and your shooting percentage. But that's conditional on being selected, because the shorter players are compensating. They're awesome in other ways. So almost certainly what's going on here is that the shorter players are amazing in other ways, and the taller players, well, they're less amazing in those ways. But they've all been drafted because they're amazing players. But this is post-selection. If you condition on selection, you cannot make causal inferences about the connections between the criteria that lead to selection. They have been distorted by the selection effect. This happens within regressions models, and that's what I want to show you next. So this is when nature does the conditioning for you. Nature is conditioned on a collider in this case, and we don't get to see the shooting percentages of players who are no longer playing basketball. Yeah? But sometimes we do the selecting inside the regression model, and it fools us just as strongly. Well, I want to say in this case, nobody's fooled, right? You see this graph and you know immediately that you've been tricked, because of course being taller is an advantage. Yeah? All of these players would like to be taller. Okay, let's do an example where it's the statistical model that's conditioning on the collider and creating a confound. So this is a simulated example, but it comes from an empirical literature. And I want you to imagine this causal graph at the bottom. We're interested in happiness, say. We're happiness researchers. We're very happy, and we want to know what makes other people happy. And we want to figure out why people are sad, because we want to make them happier. That's a noble goal. I think this would be good science. Yeah? And so imagine it's true. This is a thought experiment to show you how tricky colliders can be, that getting married is both positively associated with happiness and age, causally. Why? Happier people are more likely to get married because they're nicer to be around, maybe, right? Happiness causes marriage in that sense, right? And also, age causes marriage. You're like, what does that mean? Well, the more years you're alive, the more chances you have to get married. So age causes marriage. The older you are, the greater the probability of being married. Yeah? Those are two causal effects, and they go together. Now, our question as a happiness researcher is we want to figure out if there's any causal impact of age on happiness. Do people get sadder as they get older? Right? And this is something you'll see in this literature. This is how this came to my attention, is people trying to interpret that effect, that there's a negative correlation between age and happiness. Here's a simulation where it's totally spurious and arises from this causal graph. So the code to do this is in the book, and this is a case, most of the simulations in this chapter are quite simple. I just simulate from like R norm. I'm just pulling out random deviates. This one's different, and so I wanted to show you something different. This is an agent-based simulation. Here I create a population of little happy people, and they age, and they get married, and they live little lives. And then they don't die. At age 65, I send them all to Spain. Nobody dies in this simulation. Spain just fills up with happy people that never age over 65. Right? It's true, right? So I've been to Spain, right? So here's the algorithm for the simulation. 20 people are born each year in this population. There's uniform happiness at birth, and your happiness never changes. What do I mean? Happiness is distributed between 0 and 1. When you're born, you get assigned a number between 0 and 1, and that's your happiness. And so of all these 20 people born, each person gets some evenly spaced happiness, right? So there's a uniform distribution of happiness in the population, and your happiness never changes. Now I know this is not real, but this is what I'm showing you, is the hazards of inference, right? The reality is more complicated, and it would be even harder to figure out what's going on, right? That's the point of these examples. At 18 years old, you're eligible to marry, and then you have your first coin flip chance. Your probability of getting married in this population is proportional to your happiness, which remember is constant, but your age is not constant. Age itself, the number doesn't cause marriage, but each year you're alive, you have another chance to get married, and that chance, which is constant, is a function of your happiness. Does this make sense? Married people remain married unto death, right? I have no divorce. That'd be a secondary process. If you're in, the code's here. If you want to play with that, feel free. And then everyone moves to Spain, okay, at age 65. Yeah. So there's this function called sim happiness in the rethinking package, which does this. You can peek at the code, right? It's not that complicated, actually. It's just a big loop where I loop over these steps. I set the seed to 1977 just so you can replicate my exact numbers, but there's nothing special about that. This is just so you can get my exact numbers back. And I simulate 1,000 years, so the population's at equilibrium. Right? There's no burn-in effect here. This is at an equilibrium, steady state, age distribution and everything. And then we get a data frame, 1,300 observations, which means there's 1,300 people in the population. And we have 3 variables. This is a cross-sectional sample of 1,300 people after 1,000 years. And then we run regressions on them, because we're social scientists. That's what we do. Right? And here's the statistical model. We're going to run a regression where we take happiness, and we put in both. We're interested in the association between happiness and age. So happiness on the top line is the outcome. And then in the linear model mu, we've got a slope B, capital A, for the slope of age. And then A is the individual's age. That's our target of inference. That's the exposure that we're interested in. But we also think, well, we know the marriage status of people in this population. We should control for that. That seems like the right thing to do, doesn't it? It's the wrong thing. The narrator, that's the wrong thing to do. Right? But I want to show you that that's the case. So I've created an index variable. Now, MID, which is your marriage ID. I think it's 1 if you're single and 2 if you're married. You can be other statuses, right? There could be other things too. We could have divorced, and that could be a third status, and so on. And then we put that in as a control. It seems reasonable. This is a multiple regression. Look what happens. It turns out, single people, which is A1, are less happy on average. See, the posterior mean is negative, and the whole compatibility interval is also negative. Right? Single people are less happy on average in this population, even though you know from the simulation that happiness never changes. Right? But single people are less happy. Why? Because happiness causes marriage. Right? It runs the other direction. It's not that marriage causes happiness. Right? This is why I kept saying, starting beginning of this week, regression models don't have arrows. They just measure associations. The causal model is separate. The arrows are something that's not in the Bayesian network. This model is on the screen is a Bayesian network, but it doesn't have directionality. So that's what the DAG does, is it imposes directionality so that we can interpret what's going on. A2 is married individuals, and now this is very positive, right? Married individuals are on average more happy, and you know why? Because happiness causes marriage. Right? The arrow's going the other direction, but the model picks it up. No problem. The Bayesian network has done its job. Now the target of inference, the slope with age is negative. Solidly negative. That whole posterior distribution is below 0. very solidly. The old are unhappy. It's a very sad south coast of Spain, right? No, it's not. There's no. This is a spurious correlation that arises from conditioning on a collider. So let me explain it to you. I'm not done trying to explain this. I know how weird this is. What has happened? Okay, let's look at the population. Now you know this is spurious because I gave you the algorithm, right? You can simulate it yourself. You know there's happiness never changes, so it can't go. Happiness does not decline with age. But conditional on marriage status, it definitely does. That is, if we stratify by marriage status and we look within each group, married or unmarried, there is a negative correlation with age. Here's the plot to demonstrate this. So this is the simulated data. This is the after 1,000 years. This is year 1,000. Each point on this graph is a person. Remember, every year 20 are born, so there's 20 individuals in each column, and every year they move to the right one step. Yeah, the last step ages off to Spain, and then 20 new ones enter the population. Yeah. Happiness is uniformly distributed and constant, so you just move to the right every time step, but sometimes you become blue, which actually in this means that you're married, right? And so blue filled circles are the married individuals, and the open points are unmarried individuals. So you'll see starting early on at age 18, the blue points are only at the top because those are the happiest individuals and their probability of getting married is highest. But over time, individuals who are less happy, only sort of median happy, will also get married because they've got a lot of years to find the right, also median happy person to pair up with. And by the end, by 65, when everybody's ready to go to Spain, sorry, I'm getting kickbacks from the Spanish Tourist Bureau here. It's very nice in Spain. Most of the population in the simulation is married by then. Yeah. Now, if we draw regression lines through both of these subpopulations, you can see there's a negative correlation between the average happiness and age. Right? The average happiness in married individuals at age 18 is very high. The average happiness in married individuals by age 65 is, well, right in the middle. Right? It's the average happiness in the whole population. Likewise, the average happiness at age 0 is, well, 0, the average happiness, right, on this standardized scale. It's just the population average, but then it declines among single people because the happier ones are migrating to the other subpopulation. But the distribution of happiness has not changed in a single person in this population at all. We have been tricked by the collider. So let's look at the diagram again and try to bring this home. So here's the causal diagram again. Remember, marriage status is a collider of happiness and age. There are 2 arrows entering, no arrows leaving. If we condition on it, we allow information to flow from age to happiness. And we end up concluding that this arrow with the question mark on it is real and it exists, but it doesn't. Why? How do I know that? Because I wrote the simulation. Right? In reality, we never know. But we have to entertain these scenarios and use information external to the data set to present persuasive causal arguments about these effects. Does that make sense? I think collider bias is super cool. It's not just here to terrify you, but a little bit of fear is good, though. Keeps life fresh. Let me give you another example. I like collider so much. I have another example. This is one I call the haunted DAG. Colliders are so powerful that they can even occur when you haven't measured one side of the collider, It can be an unobserved confound and you can still get collider bias. Isn't that cool? So let me show you how that works. So this is like haunting. So in my subfield, human evolutionary ecology, we're really, really interested in allopaternal effects. That is, grandparents and Luke knows about grandparent effects. Sorry, I shouldn't have said anything. I know you want to leave that behind. But no, it's a very important question. What is the material benefit of having grandparents? Humans stack generations together, and typical human families have 3-4 generations living together. And there are resource flows, and there's also information flows between the generations, and we want to figure out how important those things are to human welfare. So people in other fields are interested in these things too in terms of educational and wealth transmission effects. You don't only inherit from your parents, but also from your grandparents. Your grandparents can influence your attitudes towards education and affect your wages. All those things are plausible. How do you figure this out in an empirical study? So imagine a situation where we've got grandparents, we've got triads of individuals we've sampled, and we're looking at something like educational outcomes, how many years of education they complete. We have G grandparents, P parents, and C children, and we consider all these arrows are possible, and we want to measure each of them. That is, there's an indirect effect of grandparents, because grandparents, well, they educated their own children. They influence their own children's education, attitudes towards education by having books in the home, whatever it is that you think makes this work. And then they can pass that on to their own kids. So that's the indirect path from G to P to C on this graph. You see that? And then there's also a potential direct effect where grandparents do babysitting and they tell their grandkids how important it is to study and all these other things that they won't listen to. Yeah, no, I mean, it's plausible that that arrow exists and it really matters. It is. The problem is trying to measure it. This is a big problem. There almost certainly, I should say, is one thing you get if you run a regression like this in the literature is you sometimes find negative effects of grandparents. That it will look like grandparents are either doing nothing or they're actually hurting the educational outcomes of their grandkids. That is, that direct path from G to C will have a negative path coefficient on it. What could that be other than grandparents are toxic? Right? And it could be collider bias. So let me show you how it could be collider bias. It's plausible that parents and their children share unobserved confounds that are not shared with the grandparents. I'm going to write this down as a variable u. U in these diagrams means unobserved. It's some unobserved confound. And you have to imagine that whenever you do an observational study at least, but also many experiments, that there are u's all over the place. So there are potentially a bunch of them. And you want to think about how they can interfere with your inference, right? So in this case, this would be something like a neighborhood you live in. Do you live in a neighborhood where the neighbors are really into education, it's a good neighborhood, has a good school, right? That's a big effect. Both in Germany and the United States, school effects and neighborhood effects are really powerful, actually, on educational outcomes. And so, even though you haven't measured U, it makes parents into a collider. Do you see that? Because two arrows enter. Now, if we condition on parents, so you're trying to measure the direct effect of grandparents on their kids, but you realize, of course, that there's this indirect path through parents, and so you want to condition on parents to control for parents. But when you do that, you create collider bias. You lose or you lose in this graph. There's no winning in this graph, I'm afraid. Sorry, I'm going to build you up here eventually. We'll come around, you'll feel better. So it becomes a collider, and we condition on both. So we simulate this. 200 triads, I assume, so BGC set to 0 at the top, you see that? I'm assuming that the direct path from grandparents to kids is 0. They have no effect. I'm just assuming that for the rhetorical advantage here. You can make it any number, you'll still get a distortion, but it's clearest when I set it to 0. And then I just simulate using this graph as if it was real, and then you run a regression, and what happens is we end up inferring down at the bottom. So this is a multiple regression that includes both parents and grandparents on child outcomes. You end up concluding that grandparents hurt their kids. There's a very strong negative partial regression coefficient between grandparents and kids, but it's entirely a result of collider bias. Entirely a result of collider bias. How does this work? So this is where we're going to bring it all together. Conditioning on a collider opens a path. So in the other two kinds of paths, in a fork and a pipe, if you condition on the middle thing, you close the path. In a collider, conditioning opens the path. It's closed by default, right? And so this opens a path from G through the unobserved variable. The fact that you haven't measured it doesn't mean it doesn't matter. To C. And this creates a spurious correlation. Isn't this cool? Okay. It is. It's super cool. So one way to think about this is what's happening when you stratify by parents is this is what the simulated data look like. So on the left, I'm plotting grandparent education by the grandchild education. Bad neighborhoods are shown in black. Good neighborhoods are shown in blue. And then I filled in all the points where the parent now, who's not on one of the axes, but the parent, and it's in a particular stratum of education. So this is what conditioning on parents does, is it stratifies by different levels of education, and then the regression only looks within each of those. That's how multiple regression works, recall. And so if we look at parents between the 45th to 60th centiles, this is what I've shown, and we draw a regression line through it, it's negative. And that's why you're getting a negative effect of grandparents. Why is it negative? I know this is like, if you're confused, that means you're paying attention, and I thank you for that. Why does this happen? Okay, so let's focus only on the parents that are in this narrow range of educational outcomes. Parents in the good neighborhoods, to be within this range, they must have had less educated grandparents. Likewise, the parents in the bad neighborhood, to have the same educational outcome as those other parents in the good neighborhoods, they must have had more educated grandparents. Otherwise, they wouldn't have the same educational outcomes. There's no way this batch of parents could be tied and have their neighborhood differences unless they had different sets of grandparents. And that's where the grandparent effect comes from. But it's because of a collider. It's because there's two ways to end up being a highly educated parent. Either you're in a good neighborhood or you had an educated parent yourself. Both of those arrows enter the P box, the parent box, and that's why it's a collider. Does this make sense? It makes a little bit of sense, right? So if you'll go home and make a cup of coffee or Red Bull and sit with this example and work through it, you can understand this. These effects are incredibly commonplace. Let me try to bring this all together. I know this is confusing. There is a framework that unites all these examples, and it's called the backdoor criterion. This is due to Yuta Pearl, who's a computer scientist at UCLA. Published this book in 2000, 2001, Causality, and which lays out this framework. The backdoor criterion is the idea that if you want to figure out the true causal impact, to deconfound a graph, you want to figure out the true causal impact of some exposure on some outcome, then you need to shut all the backdoor paths from that exposure to the outcome. Right? There's a forward path, so-called front door. Right? So in this example at the bottom, we're interested in the path from E to W, but there's some unobserved confound that creates a backdoor path because there's an arrow entering the back of E. And we have to shut that. We have to slice that arrow off somehow in order to infer a true causal effect. When you do an experiment, that's what you do because you set E by playing God. That's how experiments work. And so you shut all the backdoor paths when you do a proper experiment. By definition, you cut all the arrows entering the back of the variable. That's how randomized experiments work. But in observational studies and bad experiments, which is, let's face it, a lot of experiments, because if you do human science, let's face it, you can't randomize all the stuff about people. It's unethical. You just can't do it. There's lots of stuff with people you could never do ethical experiments with. And so these backdoor paths exist, and so you want some set of criteria for which variables you could include that would shut all the paths. And that's what the backdoor criterion tells you. And this brings us back to ye olde causal alchemy, the 4 elemental confounds. You know how to, with each of these are the only ways that variables interact together in these graphs. And you know how to shut each of them. The only one I haven't explained so far is the descendant, but I'll explain that. So very quickly, looking in the upper left with the fork, this is an open path unless you condition on Z. Right? So if this is a backdoor path, then you need to condition on Z to shut it. Likewise with the pipe, that path will be open unless you condition on Z. So if it's a backdoor path, you want to condition on Z. Does that make sense? And then with the collider, this is closed until you condition on Z. So if that's a backdoor path, leave it alone because it's already shut. Does that make sense? And then finally, the descendant. If you've got a descendant here like A coming off of Z and you condition on A, it's like weakly conditioning on Z. It's not exactly the same, but since A and Z are correlated, they share information. And if you condition on a descendant, you can partially shut a path. So you have to be prudent about that too. What is A like? It's like a proxy. You can't measure the thing you really care about, but you measure something that you think is correlated with it. You have to be just as careful about conditioning in those cases. Yeah? Does this make sense? Okay. We're running out of time here, so instead of rushing through any of this material, I've got some examples where we're going to play with these examples. I'm going to show you some causal graphs when you come back on Monday, and we're going to exercise the backdoor path on them. We're going to look at them and we're going to see, are there confounding paths here? What's the minimal set of variables we need to include to remove all the confounds? So we'll run through some examples together in class on Monday. All right, you have some new homework. Let me rush forward to the new homework, sorry. There. Okay, there's new homework. It's already online. It involves foxes and a causal graph. That's a fox. And a causal graph. And I'm going to ask you to make inferences in a multiple regression in light of the graph. And then next week, I'll finish up with backdoor criterion, and then we'll start talking about overfitting. Okay? Have a good weekend. Enjoy the snow.